Hello, my name is Wali Mateen, and today I'm going to be presenting my undergraduate research project on the thermoelectrical and thermomechanical study of electronic interconnects with solder and solder paste. I partnered with Michael Morrison to conduct this research under the advice of Dr. Mohammad Khan. Today I'm going to be presenting on behalf of both me and Michael. But before we get into this research presentation, I just want to talk a little bit about why this research is important. When we turn devices on and off, they cause the copper traces on the circuit boards of the device to expand and contract based on the temperature of the operating device. This research aims to analyze the effects of that thermal change in the PCB and provide a way to better model the stress and temperature changes in the structure. This will help us avoid trouble in the future when we're trying to fix or predict reliability of a certain structure. So today we're going to be talking about mainly two different types of interconnect structures, the quilt packaging method and the TSV method. There are other types of packaging methods out there, but for this research project, we solely focused on the quilt packaging method and the TSV. Next, we're going to be talking about the materials that we used in the simulation. This is going to consist of all the different solder compositions that we have used so far for the structural analysis and the materials surrounding the interconnect area, including the copper and the silicon substrates. Next, we're going to be presenting the simulation results conducted on these structures by applying different materials and running different amounts of current through them. Next, we're going to be having a brief discussion on what we have learned from the project so far, and then we're going to do a conclusion and summary to highlight the learnings, the findings, and the future possible steps for the project. On this page, we're going to be talking about the quilt packaging method. On the right side here, we can see that there are two silicon substrates with copper traces and nodules sticking out from the side. These nodules are basically copper blocks that are extending from the body of the silicon substrate and then interfaces with other nodules from other silicon devices. These are very efficient at ultra-high bandwidth signal transmission and causes low power dissipation and has a higher silicon efficiency. On the left side here, we can see the zoomed in version of these nodules. We can see that the majority of the nodule is made up of copper with a very thin layer of solder or tin at the edge here. We could also see an oxide layer resembling a shell right outside the copper block. This is created due to some chemical reactions between the silicon substrate and the copper. Here we can see the structure that was designed and created for the simulation. It resembles the quilt packaging method discussed in the previous slide. As discussed before, we can see two silicon substrates sitting on a carrier where the nodules are connecting the copper traces of the two different substrates. On the right side here, we can see a zoomed in version of the nodules and even more zoomed in version or a microscopic image of the nodule itself. Here we can see the chips on both sides with the nodules in the middle. So on this page, we talk a little bit about the parameters or the important parameters of the solder compositions used for the simulation. As of now, we have only had a chance to test two different solder compositions, but are in the works to test more. This table should grow by at least 4 times by the time we're done with the research. As of right now, we have done research on lead-based solder, where there's 40% lead. And then the second one here is bismuth-based solder with 58% bismuth. We include the Young's modulus, the Poisson's ratio, coefficient of thermal expansion, and electrical conductivity. We do have other parameters, but these are the most important ones for the simulation. So here we talk about the quilt packaging structure used in the simulation. As we can see here, there are two silicon substrates with nodules in between them. If we take a closer look here, we can see that there are nodules of various widths along the edge of the two silicon substrates. Taking a deeper look at them, we can see that one of those nodules is 200 micrometers wide. This is generally the ground trace and is used as a ground between the two chip structures. These are generally made with copper with a thin layer of solder in between them, usually 1 micrometer thick. Here we can see a table as a legend for what materials are shown in this figure on the left here. We can see that the silicon is represented through gray, the copper as a reddish brown, the solder as a light gray, which is barely noticeable here, the epoxy as white, and the FR4 as the green material underneath here. The FR4 is the material that printed circuit boards are made of. So after we assign different materials to the domains of the structure, we can now run tests. We do this by changing the properties of the solder in there, and therefore changing the composition of the solder, as well as changing the amount of current that passes through the structure itself. So here we can see some additional data points on what temperatures we have observed when running simulations with different amount of currents running through the structure. We can see that as the current increases, the temperature in the structure also increases. But we can also see that even though the two solder compositions are different, the temperature caused by the current is roughly the same. So far, we have only been talking about the quilt packaging method. Now we're going to talk about the through silicon via, or the TSV method. Looking at this figure right here, we know that there is a copper trace running through the middle of the silicon substrate. If we look at the zoomed in version over here, we can see the trace exiting to the surface and then connecting to another copper rail mounted on the surface through a solder bubble. We can test different properties of this structure by changing the solder composition of this bubble, as well as running different amounts of current or voltages across the contacts. Here we see a diagram representing the stress caused by the electrical currents flowing through the contacts, or nodules. This simulation was done with the nodule set to 90 degrees Celsius, with the ambient temperature set to 22 degrees Celsius. The figure shows a von Mises plot of the structural deformation of the structure. And here on the right side, we can see the different stress distribution based on different operating temperatures of the traces. All of these were set at 22 degrees Celsius ambient temperature. So even though the project is not completed, we can form some reasonable conclusions based on the data that we have already received. The first conclusion that we can make is that the temperature did not change significantly with the different solder compositions. We can see this in the simulation data. We can see that as the current rises in the structure, the heat also rises, but with different solder compositions, the heat difference is very minute. Next, the current that was simulated in the structure was DC current. Later on, we will work to simulate AC current, which will more accurately predict the dielectric losses and electromagnetic losses. The next conclusion we can make is that since the temperature change caused by the electrical currents weren't significant, the hotspots in the chips themselves could cause the high temperature required to damage the interconnect between the chips. Finally, this simulation or structure would only be applied for the specific interchip interconnect structures mentioned, but could be also applied to other joints as well. In the future, these results of the simulation can be used to more effectively model the failure of different interconnect structures. Here is some references that credit towards the various resources that were used during the making of this presentation and through the process of this research. I'd like to thank the Electrical and Computer Engineering Department at Saginaw Valley State University for providing me with a research lab so that I can work on this project. I would also like to thank the undergraduate research program here at Saginaw Valley State University for funding my research and making it possible for me to gain new experiences and dive deeper into the world of interconnects research. And finally, I'd like to thank all of you for sitting through my research presentation and learning a little bit more about the effects of solder compositions on chip interconnects. If you have any questions, please feel free to email me and I'll respond as soon as I'm able to. Have a great day.